boards are almost dry. Start up there. Good. So. What we'll do today is a Cauchy homology and a model for computing the homology, or really the cohomology of the free loop space. On a space. Manifolds not necessary. Okay, so to talk about Cauchy homology, we have to go to the world of algebras. So we will be doing algebras. In the end, I'm gonna end a field anyway, so we'll just not worry about things and take a field from the beginning. So K is going to be a field. I think Q or R could be. I think today it can be a finite field. Tomorrow it cannot. So, anyway, in the end will be rational. And we need algebra. So definition: differential graded algebra, DG algebra, is a chain complex A with a differential. Really, should I say this more clearly? A is it's not necessarily positively graded. So A is it has a degree. It's a sum over n in the integers for me. A n. Okay, I have a sum of vector spaces. It's a graded vector space with a differential. This means d square is 0. Okay, so that's a chain complex. And then I want a chain complex with a multiplication. Being an algebra means that I have a multiplication. So I call it M here. M goes from A, tensor A to A. I put in the exercise, how to make this a chain complex. This is a chain complex again. If this was a chain complex, this is again a chain complex. This should be a chain map. This means that it commutes with the differential. Means if I first do differential here, and then my multiplication is the same as if I first multiply and then differential, okay? It should be a chain map. And so it takes, two elements, A, tensor B, I'll just write A times B. So it's a linear map, of course, right? Chain map is also a linear map. So A tensor B goes to A times B. That's the definition of a differential graded algebra. Okay, happy with this? We'll work all hour with differential graded algebra. Algebras, no, it's not the definition. Okay, I want to know two things about this map. One is important, it's associative, the multiplication. Okay, which is associative in the usual sense. A times B times C is A times B times B plus unit cell. Also usual cell, what does it mean here? That is, there exists one which is a degree 0 unit, so it lives in A0. It's a degree 0 element in A, and it plays the role of a unit. If I multiply with 1, it doesn't do anything. Okay. So this is not strictly speaking necessary, but it will be for me at some point. So I will all the way through have units. Yes.
How does the multiplication behave with respect to the grading?
It's degree 0, so that means it goes. So M goes from A P to A Q to A P plus Q. Yeah, a degree 0 multiplication for me today. Examples. A could be A could be just all in degree 0, could be, for example, the simplest example is A is the field itself. All in degree 0, D is 0, M is the multiplication of the field. Okay, this is a happy differential graded algebra. It's not very differential and not very graded, but it's still a differential graded algebra. Okay, I could do something more complicated. I could take A is, but still not too complicated, A is kx, where I set x in some degree D. Not D. Call it K. No. Something else. Some other letter. Okay? What does this mean? This means that, and D is still 0, for example, right? What does this mean? This means that, well, A is really, A is 0, where I have K, plus A R, where I have K times X, plus A 2R, where I have K times X, because I'm doing a polynomial algebra. This is K times X, this is K times X squared, and so on, because blah, blah. Okay? So that's a polynomial algebra with a grading. So it's spread out. Or I could, truncate it. I could do modulo, for example, x squared is 0. So these are fine, happy polynomial algebras. This will show up, so let's write it down. K x mod x squared, this is like A0 plus AR, right? And this is generated by 1, generated by x, and x times x is 0. And 1 times x is x, and 1 times 1 is 1, and so this algebra. Yeah. Something with a differential, maybe. If I talk about differential graded algebras, we have seen, for example, a differential graded algebra. X is a space, and I'm going to take A to be co-chains of X, but I'm going to write them backwards because my differential goes down in degree. This is why I also wanted to allow any grading here. I'm allowed to go in the negatives, so I'm putting C0 X and then C1 X here in spot -1, and then the differential goes this way in the cochains. Okay, so that's a chain complex, but we've seen it has a multiplication. We saw the cup product. Okay, the cup product M is the cup product. This was a degree 0 multiplication. If I put a minus sign, it's still correct. We saw CP tensor CQ goes to CP plus Q, so C minus P, plus C minus Q goes to C minus P minus Q. It's fine. I'm allowed to do that. And I also want this one because it will also show up. So I could also take the cohomology of X. So A is now the cohomology minus, again, of X. And again, with the differential is 0, and the product is the cup product. The cup product is also defined on cohomology. This is now just a graded algebra. The differential is trivial. Yeah.
Why are we changing the grading right now?
You'll see in...
Do we want D to have the
you will see that this is what it is. What can I say?
you always think of
Will you see this? I don't know. It shows that, you have to decide in what way your differential goes. And I want my differential to decrease degree. So I could take them up, but then I have to reverse another grading later. So I choose to reverse this one. Because otherwise, I'll be creating a double complex, and it's somewhere I have to call one of the degrees minus. Or I have to do, I don't know. I mean, I don't have to, but I want to. Yes?
So you always think of DGAs as having a decreasing degree?
I do, but you don't have to, right? There's no reason. It's yeah. I just want for today and tomorrow, and from me to have different decreases degree, but you don't have to. No. Sorry about this. It's not such a big problem. Good. Yeah, I should say, yeah, there's a relationship between this and that. Note, which is why we axis say, oh, well, I did anything. So the R dimensional sphere, the sphere of dimension R, then the cohomology of X, this with the coproduct is actually that thing, K X mod X squared, right? The cohomology of a sphere, so I put it like this as R, the cohomology of a sphere has a class in degree 0 and a class in degree R. So it's something that looks like this. And what is the coproduct of this guy with itself? Well, it better be 0 because there's nothing higher up, so we don't have a choice. And I say this is the unit, and that's it, right? You have computed.
Thinking of in degree minus, really?
Yes. Minus. Yeah, sorry. Yeah. X in degree minus. Okay. Now you're getting to tell me that, but it's yeah. R could be negative. Minus R. Thank you. Okay. Let's not worry too much about this minus sign for the moment. Good. So when you have a differential graded algebra, you can create something which you can get a new chain complex. Is it me? Can get a new chain complex. Okay, a new chain complex which is called the Hochschild complex. So let me define it. So we start with A, D, and M, right? We have an algebra, a chain, a differential. Let me call it dA, the differential of A, and a multiplication. Define a new chain complex. I'm going to keep the usual notation, even though it's today I'm going to write AA because that's the way we write it. It's the Hochschild complex with coefficients in A. You could put something else here we want, but so that it's the same as what everybody else writes. And it's a chain complex, so this should be a sum of things. It's a sum n greater or equal to 0 R. I need something A bar, A tensor, A bar tensor n. So what is A bar? If I have my unital differential graded algebra, I have K maps into A by doing times with the unit. Okay, the unit goes in here, and I can quotient that out. A bar is A modulo this map. 1 times the unit, okay? We can do this. It's a vector space. We're doing vector spaces. This is as a graded. Didn't tell you what the grading is. As a vector space, that's what it is. The differential is a sum of 2 differentials. So D is dA plus dH, I'm going to call it. I have to say what the grading is, and I have to say what the differential is. Okay? So what do elements look like? An element in here is something like this. A0 tensor, well, it's a sum of things like this, right? But the generators are like this. A0 tensor AN. And because I killed one, AI is not the unit. I can write it as AI is not 1 for I bigger or equal to 1. Okay, that's what you should think of. Elements are things like this, and we'll say that this has degree of A0 plus degree of AN plus N, where of AI is the degree of AI in A. Okay, so everybody here has a degree because they live in A, and A was graded, and now to that sum of degrees I add N. Okay, I'm allowed to do that. Yes? No? Yes?
I don't really. Can you say more about what A bar is?
About?
What A bar is?
You quotient. You quotient. Think this is. You quotient out the unit. you collapse. You do a quotient. This is a sub vector space. It's a happy vector space. You can just
if your A was say
typically,
kx,
yeah.
then you'd have
You just
an
remove
arbitrary element of kx, and then you'd have non-zero powers, n non-zero
Yeah.
powers.
So in I would just kill this in this case. I would just kill A0. Typically A0 is just k, and you just remove k. You take one less copy of k in however many. In A0 you have at least k times the unit, and then a bunch of other stuff, and you remove.
Okay,
You
so
kill the guy.
from A0.
It's only in A0 this thing. Yes. Yeah. Yeah. We will compute. We will do this part of the computation in this case in a bit. Yeah. Yes.
Did you say what these H is?
No, not yet.
Okay.
Yes.
So why do you have M?
Why? I don't know. Because it's the right thing. So the funny thing. So where am I going? Right? At some point I will relate this to the loop space, to the homology of the loop space, and we have to add n in this case. But this is not where it comes from. It comes from algebras. This was invented as a homology theory for algebras at the same time as people were working with homology theories for groups, and so doing some. So it's right in some other sense also, but it fits our purpose. So I have to define a chain complex. So this is what my graded vector space is now, and I'm going to tell you what dA and dH are. dA, you know what it is. This is the differential induced by is the differential induced by A. So what is it on the tensor product like this? dA of A0 tensor. Let me write it once so we have seen it. AN is going to be a sum. I goes from 0 to n of, well, there's a sign. I'll write it in a, well, no, let me write it. A0 plus AI minus 1. And then you go A0 tensor AI minus 1. And when I get to AI, I take a differential in A, right? dA of AI tensor, and then I'll leave the other ones as such. Okay, so in the exercises, I let you work out why there should be a sign. But this is the sign for this differential. So we do this. We take the differential at every place. So this decreases the degree by 1 because our degree took into account these degrees. So it goes down by 1. And now here's the other degree, the differential dH of this guy, A0 tensor blah 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 AN. So it's first a sum. I is, I guess, 0 to n minus 1, I want to call it, 0 to n minus 1. And then I'm going to go, minus 1 to the I plus 1. This is the easy sign. A0 tensor AI plus 1 tensor AN plus minus 1 to the, this is more complicated, n plus 1 plus, it's not too complicated, AN goes past A0 plus AN minus 1. And then I go AN A0 tensor A1 tensor AN minus 1. First, this makes sense. I'm using the multiplication of my algebra. I have a multiplication. I'm using, I'm multiplying side by side everything cyclically in a. So the last one, when I would like to, the last one I multiplied to the front one by moving it in front and multiplying it. But otherwise, so I do this side by side multiplication. When I do a multiplication, n goes down by 1. Okay. So now my degree, it goes down by 1 as well. Okay, so it's this one that goes down now, because the other one doesn't change the degree. The multiplication doesn't change the degree. Total, the sum of the degrees. Okay, so it makes sense. So I claim you can do this as a differential. Well, I should say a little bit careful. Okay, facts. We have to be a bit. Facts. First, dA square is 0. So this is a standard thing. This is what in the exercises. Standard thing, this is a differential again, if I do this with these signs. 2, dH square is 0. Well, you have sort of done this. So here's the claim. Claim dH is a sum minus, well, actually I put a minus, an extra minus sign. So minus dH is a sum minus 1 to the I di. And these are simplicial. They verify the simplicial identities. It looks quite a bit like things we've seen, right? I'm doing something here, then something here, then they satisfy the simplicial identities, and therefore they square to 0. You have done the exercise yesterday. Okay? So this H is also 0. And then third claim is the A and the H commute is equal to the H dA. This is pretty obvious modulo if you believe my signs. This is just because this is true for each di. And the multiplication is a chain map. I'm just using the fact that the multiplication is a chain map. Okay, that's what I'm doing. So therefore, dA plus dH squared is equal to dA squared plus dA dH plus dH dA plus dH square is 0. Okay, that's what I was writing my notes. I got to that computation and I went, oops. Where is that bloody sign? Forgot one sign somewhere. Okay. So no, it's not 0. I have to, well, plus minus here, right? I have to be careful how I define this, right? So this is also in the exercises, when really what we have is what is called a double complex. It's a chain complex with two gradings. I have a grading here and I have a grading from the algebra. And I have two differentials and they commute. I can define a total complex exactly as I've done. I take the sum, the degree is the sum of the degrees. That's what I wrote. And the differential is the sum of the differential, but I have to put a sign, otherwise it doesn't work, right? And the sign, what works is, d a. Let's call it. We could call it still plus, right? But I mean, of A0 tensor, blah, blah, blah. You have to do you have to choose, you make a choice, right? And so we can do it dA of it plus minus 1 to the n dH of it. That works. So if I have a sign that depends on, my sign has to depend on one of the two degrees. Either way works. Okay, so this will be my sign. I'll put maybe the other sign. I don't remember. Doesn't matter. I put the other sign in my notes. I put it the other way around. So minus. So let's do it the other way around. So then I have the same dH. We do dH of this plus minus 1 to the degree of A. So A0 plus AN. dA, okay, of the same. So that's a.
When you say M is a chain map, do you mean it satisfies the usual Leibniz rule, sort of graded Leibniz rule with sign?
Yeah. So this is what I, look. Let's write this down, right?
So if you commute it, how you get generally.
Yeah. So d of A tensor B in A tensor A, by definition is dA tensor B plus minus 1 to the A degree of A tensor dB, and so d of a product A times B has to be the product of dA B and with this sign. Yeah, that's what it means to be a chain map. Yeah. Good. So we made a new chain complex, and we agree it's a chain complex. Got so far. So definition, this is the Hochschild complex, so that gives the Hochschild homology. So definition, the Hochschild homology of A, this DG algebra, so differential graded algebra, A, D, M, is the homology of this, right? H, H, A, A, we will usually write it, is the homology of this chain complex, C star, A, DA plus DH. Okay. And lost an eraser. Good. Yes. So, yeah. Shall we do this one example? If A is in just in degree 0, so this also works for just algebras, which are no grading, no differential. Okay, I can restrict to these guys. Then, if we try to compute what is H0 just for fun? What does this mean? To take the homology HH0 of A, I have to take the kernel of the differential from C0 to C minus 1, but there's no 2. So, because I have no degree, all my degree is the Hochschild degree, and I have nothing in C minus 1, so there's 0, so everything is in the kernel. Okay? And modulo the image of D from C1 AA to C0 AA. Okay? That's the definition of the zeros homology group. C0 is just A. Okay, so this is A, the whole of A. Modulo, what is this? This is A tensor A. And what is the map? The map says we take A tensor A, and we take here A tensor B, or A0 tensor A1, and we multiply the first two together, and then the first one is also the last one, we put it in front. So this is, the differential is AB minus BA, right? I put the last one back in front. Yes. So, and if B was a unit, which it isn't, but it wouldn't make a difference because that would be 0. We could, whatever, don't worry about the units. So this is modulo, this is what is called commutator, right? So for example, if the algebra was commutative, then this would be a 0 differential. It would still be, so what we've done is we have killed the commutators. Okay. Is the algebra modulo all the commutators? We kill everything that did not commute, dead. Yeah?
So when you define the C star A in this chain complex, the grading is the sum of the grading of A and the sum of
Yeah. Yeah, that's the degree. Yeah. Correct. Okay, so as I said, I mean, yeah. I don't think, actually, so there's a cohomology version which gives nicer things, but for homology, as a general thing, I'm not sure it does something nice. You get for whatever, but yes. So I mean, this Hochschild complex comes from all sorts of other things, and relates to all sorts of other things. But what we are interested in is the loop space. Okay, so here's a theorem which I'll try to explain, which is a theorem of John Jones from the 80s, and it says for x1 connected, so simply connected, that means pi 0 x is trivial, 0 is, there's only one thing, pi 1x, okay, no, it's connected and it has a trivial fundamental group. X1 connected, we should also say finite type, if we formulate it in the terms I will. Finite type, for example, a manifold, so something like, so the homology of x, h, k, x is finitely generated for every k. Okay, it could be infinitely many k, but I don't want to have too much stuff. So for example, a manifold is happy, no problem. And that's it. We are over our field. Then that's it. Then if I take the Hochschild homology of cochains minus, here's my minus star x, cochain minus x. This is isomorphic to the cohomology minus Lx. Okay, it is a way to compute the cohomology of the root space. Yes.
Right, minus C minus star due to, like, I mean, I know it was something or is it just cochain, like
Yeah, so these are the cochains. These are the singular cochains of X. So remember, this is the singular cochains with the cup product. With M is the cup product. Okay? Yeah?
And this was coefficients in any field?
Yeah, I think so. Yeah. Any field.
Does it
Yeah.
also work?
I'll show you where you need something, and then if you know somebody who can do this over the integers, then it does. But I don't know. It's stated a little bit vaguely in the paper, but I don't think. Yeah, I don't know. Maybe it works more generally, possibly. Okay. So before we do the proof. We heard yesterday that it was useful to know the cohomology of the loop space, the free loop space on the two sphere. Okay? Yes? Or any sphere, really. It's good. So example, we can compute the cohomology of the loop space on, now I called it R. In my notes it's M. Let's call it M. Okay? Cohomology of M. Okay, so we saw that if you want to find geodesics, you have to find a non-trivial, one way to find a non-trivial geodesic, to find a geodesic which is not a constant loop. If that is a geodesic, I don't know. You need a homology class that is not from the homology of your space, because then you cannot contract it down to your space. And Morse theory tells you that there's some critical point, and the critical point is a geodesic, so you're done. Okay, so that's cool. We can do it. So first we need a little fact. Is SM is what is called formal, which means that its cochain of the sphere is quasi-isomorphic to its cohomology as a differential graded algebra. As a differential graded algebra. So I'm not going to do this, but you can believe this. Why do we believe this? Because there's so little homology that somehow, what one does is one goes through minimal models. This should be a minimal model for the sphere is really nothing, right? So M is, by the way, always going to be at least 2, even though this is not a problem right now. Because we need a simply connected space to apply the theorem, okay? So I'm going to use this, that they are quasi-isomorphic as differential graded algebras. Now, look at what I've done with an algebra, differential graded algebra. I created a chain complex, there's this chain stuff and so on. If I have another algebra which is quasi-isomorphic as a DG algebra, that is, I have a quasi-isomorphism which respects the multiplication, I will get a quasi-isomorphism of these chain complexes, right? So the Hochschild complex won't depend on the quasi-isomorphism type of DG algebras. So this implies that the Hochschild homology of C minus star SM, C minus star SM is simply isomorphic to the Hochschild homology of the cohomology minus of SM. Okay. There's a map, which is a chain map, which induces an isomorphism on homology. Okay. Yeah. It's like homotopy equivalent, but for chain complexes. Okay, so to compute this guy, I just have to compute this guy, and then we say, hey, great, because this one was very small, right? Remember, this was just k x mod x squared with x in degree minus m. We got this right. Okay. But we need the. Leave this. Okay, so let's do it here. So I'm going to do almost a computation. I'll leave you the last little bit. But, you know, what is this C star H minus star SM H minus star SM? What do I have in here, right? So this is generated. Let's write generators. Generated as vector space. What do I have? I have to take tensor copies of A, but I only take A modulo the unit here, right? So in the first, so when n is 0, the first thing is when n is 0, I just have the algebra, and the algebra has two generators, 1 and x, right? So I have 1 and 1 and x. This is in Hochschild degree 0. Okay. What are the degrees? Well, this is in degree 0 in the Hochschild complex. This is in degree 0. This was in degree minus m. Yeah. Now, if I have two things, well, I could put 1 in the first position, and then in the second position, I can only put x because 1 is not allowed. So I can put x, and I could have started with x. So I have x. I have also x tensor x. So this is in degree 0 plus m minus 1. So this is, 0 minus m plus 1. Okay, 1 minus m. And this is minus m, that's minus 2m plus 1. 1 minus 2m. And then I'm done with the Hochschild degree 1. So that's cool. I go to Hochschild degree 2, do the same thing, right? I can put 1 tensor, and then I don't have a choice. I have only x and x. And I could also have done x tensor x tensor x. And it keeps going like this, right? So this is now in degree 2 minus 2m, and this is 2 minus 3m, and so on. So these are the generators. They're very few. I mean, infinitely many, but very few still, right? And what about the differential? So dA, what is dA? 0, right? We took a differential graded algebra which actually had no differential. So cool, that's done. And what about dH? Well, let's look at the dH. What does dH do? It takes element and it starts multiplying them side by side, okay? What is x times x? 0 also. Note, x times x is 0. Okay, so when I take the differential, for example, this guy, it's going to be 0. Whatever I do, this is 0, right? The differential on this, d is 0, no question. D is 0. D is 0. This one goes to 0 also because there's nothing below. What about this one? Maybe. Don't know, right? The two terms, right? There's x times 1. 1 times x and x times 1, which is x. X and x. Two terms that look the same, that are totally the same. The only thing is where there are some signs, right? Okay? So the exercise is to check exercise. So d almost always 0. 0, but depends on a combination of m and n. Okay, so for some dimensions of spheres and some n's, it is actually non-zero. Well, if I work integrally, because it'll be time. Well, it will be non-zero. It'll be times 2, right? So once in a while it's times 2. The rest of the time is 0. Okay, so exercise play with the signs, write it out. If you always get 0, you got the wrong answer. If you didn't, it's probably right. Okay, but this is, this means we already have a picture of the homology of the loop space on the cohomology of the loop space on spheres, right? We basically have the classes. I'm saying in some cases this is exactly the cohomology, and sometimes you have to remove some of these if you're in Russian thing. Okay. What do we do? Yeah. And in particular, you can get this class in degree 1 that was needed for the 2-sphere, I think. Yes. Okay, so back to this theorem. What I want to do in the rest of the time is to tell you why this is true. Ready? So, sketch. Sketch of proof. This has to do with what we did yesterday. But let's go there slowly. So first, we'll start with complex. So we're looking at the Ruchel complex of this thing. This is the homology of a certain chain complex we define. So sum n greater or equal to 0 of C minus star x tensor C star minus star x bar tensored n times, and then this differential dA plus dH. So the first thing I want to do is to now remove this bar. Okay, not a big deal. Okay, one can show that up to homology we didn't need, I did this. Why did I do it? It's because I wanted this in the computation, right? Made my computation very, very easy. Otherwise, it's more complicated. So I wanted it for the computation, but now I don't want it anymore. Claim this doesn't change the homology. It's like we have added something contractible. Okay, so this is the first step. Once I have done that, look at this. So this becomes. Am I allowed to just rewrite this? Are you going to kill me? Oops, maybe not. Let's try this. So this is this tensored n plus 1 dA plus dH. Okay. Now this looks.
It's minus star.
Thank you. It's a minus here, like this. Yes. Okay. So this looks quite a bit like the following. So isomorphic, maybe to the homology of, what about we do a chain complex that looks like this, C minus star of x to the n plus 1 instead. And some other differential, d a bar plus d h bar. Like this. Okay. These two chain complexes look quite a bit the same. Can I do something like this? Yes, we need to do this. So we need an Alexander-Whitney map. Alexander-Whitney is a map, cochains CP x tensor CQ x to C P plus Q x times x. So I'm going to write a map. I'm writing it this way. CP, that's what I seem to be writing. Okay. I thought it was going the other way. Let's try. So there are maps both ways. There's one called Alexander-Whitney, the other one called Eilenberg-Zilber. I think this is the Alexander-Whitney. I think this is also the one I need. So let's try. And these are quasi-isomorphisms, so isomorphism in induced isomorphism in homology. I want to take alpha tensor beta to, what is alpha? So alpha is in CPX. So alpha is a map from the chains CPX to K, right? And these were the maps. So we're back to our maps and maps and maps. Delta P to X, okay? So alpha takes any map from delta P to X and gives a number. And beta does this with Q chains, right? And I want to get an alpha cross beta that goes from C P plus Q of X to K. So it's a cochain of degree P plus Q now. And what is it going to do? Alpha cross beta of sigma P plus Q. Sigma P plus Q is now a map from delta P plus Q to X cross X. Okay, it has two components. It's sigma 1, sigma 2. Okay, it's two maps to X. And we're doing like,
C plus Q of X cross X?
Yes, thanks. Cross X. We're going to do something like the cup product. You remember the cup product we were doing, evaluate on the first half and then on the second, okay? We do this, but now we have two maps and we do on the first half of the one and second half of the other. Very similar. Okay, sigma of this, it's equal to alpha of sigma 1 restricted to, V0, Vp times beta sigma 2 restricted to Vp plus Q. Okay. Yes. It's very similar to the cup product. It is so similar that they are very related, right? So note, we need this note. Remember, at some point I want to talk about the cup product because that's our multiplication here. The cup product is what? Well, it's the same thing except that I did a diagonal somewhere. So I go C, P, X, tensor C, Q, X. Then I do Alexander-Whitney, C, P plus Q, X cross X. And then I do the diagonal dual of X, C, P plus Q, X. So there's a map from X to X cross X, which is the diagonal. If I do the diagonal, what happens is these two maps, sigma 1 and sigma 2, are the same. And therefore, I am doing exactly the cup product. There is only one sigma in that situation. Okay? So equal to the cup product. This is a rewriting of. Maybe this is the definition of the cup product, really, when it was defined. What did I do? This is very useful because so we wrote a map. Seems to be going this way, right? On the level of graded vector spaces, I wrote a map from this to this. But what have I just told you? I've just told you that the cup product, which is used to define this respects this differential, right? We're talking about double chain complexes, right? We have a bigraded thing and two differential. dA is totally happy with this map. This is a chain map because this is a chain map. Alexander-Whitney is a chain map. Okay, so dA is commute with this, so this is happy. And what about dH? Well, here it's the cup product. And what have I just told you? I've just told you that the cup product corresponds here to the diagonal. Okay? So this works. I'm just exactly telling you that the cup product becomes the diagonal. So dH is same as dH, but with the diagonal for the product, right? The diagonal. I'm just going to do a bunch of diagonals here on X. Okay? This is exactly what I've told you. There is a differential. There's an obvious way of writing the same sort of chain complex using diagonals instead of cup products. Yes?
There's a term in DH which is some kind of
Man, you're too good. Wow. Okay. So this has passed. This is a theorem from the 80s, right? Has been used, and tons of references, right? Mr. John Jones doesn't say a word about this, right? Pretends no, it's not a commutative. This does not commute with the last boundary map, because the last boundary map needs to commute terms, and the Alexander-Whitney map is not commutative. Does not respect this. Okay. So this is not right. This is not a chain map. I've been almost convincing you that this was a chain map. It is not. Okay? So one of my students noticed this as he was trying to generalize this. So Massimiliano Ungaretti was, he was working and trying to generalize. It's easy to generalize. You just take the old theorem and then there's a mistake in the old theorem. Okay, so it's not too difficult to fix in the end. When you have thought about it for many months, he would kill me if I did say something else, right? No, it's true. So what is the idea? I mean, the idea is the Alexander-Whitney map does not respect. It's not commutative, but it is up to homotopy, and it is up to all higher homotopies, and we know this. So it's a question of inputting this into that map. So there is no chain map, but there's a zigzag. So it's still true on the level of homology, but this is really a zigzag. There's a guy in the middle here. Okay, well spotted. Very good. Yes.
Would you mind saying briefly again why we can get rid of the bars, the Siemens or bars?
I didn't say anything. It's.
Okay, I was writing. So that's just.
It's something normalized chain complex versus not normalized chain complex is it often happens. You should not be surprised if, because this often happens. But but you should be surprised because you haven't seen this before. Okay, yeah. But I'm saying this is not a big deal. Yeah, and this works. Yeah. Yeah. Okay, so that was step 1. Okay. We changed, but now you should already be quite happy, because now what have I done? I've taken this cup product, blah blah blah, algebra to something x to the n+1 with the diagonal. Did you do the exercise? Okay, if you did the exercise, then you should be happy. Because what was the other side? So let's go back to what we were doing yesterday. So on the other side we have the loop space. Right. Don't have the right. Let's do it like this. Okay, so we had this, right? I don't know. Well. So what we did yesterday, we said Lx is the same as the maps from the realization of this simplicial set, right? X. Okay, and then we computed what this was. So I do it. I'm gonna. What is going on? So. I'm gonna. It's easiest to tell you the truth, right? More easily. So what is really happening is the following. So S dot is a simplicial set, right? And remember, Sk was just 0 up to isomorphic to we could just take 0 up to k, right? It was just a set of k+1 elements. And that means that when I take maps from S dot into K, now I'm not taking the realization, I'm just taking the simplicial set. This becomes what we call a co-simplicial set. Right? It satisfies this, it has co-phase maps and co-degeneracies, everything is turned around. Satisfies the co-simplicial identities, because we've taken, we're dualizing when we do something like this. Okay, so there's a something going on. And what I finished with yesterday was to say that yesterday at the end, I wrote some complicated formula for the loop space, right? But what I was really writing was that maps from the realization of this simplicial set into X is equal to what is called tot of maps from S dot into X. So this is a co-simplicial thing, and this is like the realization of a co-simplicial space. And there's nothing going on in here. This is what I was writing yesterday. This is very ugly to write. Remember what it was? It was this, it was a product of maps from Sk cross delta k into X, satisfying some relations. And this is, I'm taking maps from delta k here. Here I was crossing with delta k. There's a duality going on, but these things are equal. And so this is what we were writing yesterday in some other. But what is this? What is this co-simplicial thing? What is, let's call this y dot is maps from S dot, or let's just compute yk from sk to X. Well, this is a set with k plus 1 elements. A map from a set of k plus 1 element into X is just k plus 1 element in X, right? So this is equal to X to the k plus 1. Okay, I have a canonical, once I choose my ordering, I have a canonical isomorphism here. Yeah? Computation, so this is our co-simplicial space in degree k is X to the k plus 1. And the you were supposed to do yesterday was that the boundary maps, these di's, in here, they will give you, so I'll have a map, they go the other way around now, right? So I have a map to a di to y k plus 1, which is, again, maps s k plus 1 into X, which is X to the k plus 2. And they come from this map, right? The boundary map here, di. Right? I pre-compose with these maps. And these maps, if you write them down, well, 0, k plus 1 now, what I was saying is di somewhere, it identifies two of these. It doesn't do anything at the beginning, identifies two of these, and then doesn't do anything. Well, the last one does this funny, it takes the, okay? If you dualize, identifying two of these is equal to, on the other side, it's saying, two of these points go to the same point, so backwards it will be a diagonal. So this will be a sum of diagonals. Di is di is like the I plus first diagonal or something like that, right? I plus first diagonal, except the last one that does this funny thing of copying the first to the last. Okay? So this was the exercise you were supposed to do. Yes?
Just first diagonal, you mean that you repeat the xi and xi plus 1? That you repeat two of the entries?
Yeah, you repeat two of the entries, exactly, yeah. That's really just, you can compute this. This is not a difficult computation. But so here are my diagonals, right? This is why you were supposed to be happy, because these are the same diagonals that are going to be here, right? So I have to finish with this. So now we are almost done, and so far we haven't used much. So this is the last bit that actually needs something, which is where the assumptions come in. So again, let me give you the general thing, because I think it's a little bit clearer. So we have our co-simplicial space y dot, and what can one do with a co-simplicial space? Well, I've just told you, well, you can make a new space, tot of y dot, which is this, it sits inside the maps, the products of maps, maps. This is what we are doing yesterday, delta k to y k. It's a subthing of this thing, right? Maps respecting some face things. So this is a space, okay? And then I can take chains of it, right? Chains, or homology, if you like, homology of tort of y dot. So in our case, this is the homology of the loop space, because this was the loop space, right? This tort, that's what we showed. Okay, so if we do this, we have the loop space. What is the other thing we can do with the Cauchy simplicial space? Well, remember what we were doing with simplicial spaces the other day, yesterday. If you have a simplicial space, the sum, take chains, and the fact that these maps satisfy the simplicial identities tells you that the square, or the sum minus 1 to the I squares to 0. Okay, you have done this computation. Co-simplicial space, co-simplicial identities, same thing turned around. We just take the cochains, right? So this gives me a cochain complex, like, C star y dot. This is like the sum of over K of C star y K. Okay, and it's a cochain complex with differential is the sum minus 1 to the I of the DI dual, right? Induced on the cochains. They satisfy the simplicial identities, therefore this squares to 0. It's a happy chain complex. Okay, so I can do this construction. It has a homology of, C star, of, I make, plus the differential of y, of course, right? The differential coming from here. So again, I have a double complex here going on, right? So I make a total complex as we were doing before, C star y dot dy plus d simplicial, right? And then you can ask, well, are these equal, right? Or isomorphic, right? And this is what is going on sometimes, in good cases, under assumptions. Like e.g., in our case, simply connected. Well, for us, this is where the assumptions are: simply connected, finite type field. Okay. If you can improve this theorem, whenever you can prove this theorem, the rest follows. What I've done has nothing to do with the loop space so much. The whole proof was about, I had a simplicial set, which was this S dot, and I made a chain complex out of S dot. So there's something called higher Hochschild homology. You can plug in a different chain complex, a simplicial set. You will get, you can follow this with other stuff. It has very little to do with the loop space, but you will have some assumptions depending on. So if you do higher dimensional spheres, the simply connectivity becomes a higher connectivity. It depends on the sphere. I'm done.